right, looking at the Chapter 11 review, let's start with the multiple choice. Question 1, we're going to use the following information for the next 3 questions. So, a well-known chewing gum maker wants to determine if any of its 4 flavors of gum are more popular than the other. A random sample of 80 people who say they chew gum regularly is asked to identify their favorite flavor of gum, and here are the results. So notice what they gave me is the observed counts. Okay, so it says, which of the following would be an appropriate null hypothesis for the company to test? Well, first, can you tell what kind of test we would be doing? Notice that it's just one distribution of flavors, and we're trying to see if one flavor is better than the other. So in order to do that, we want to assume all flavors are equal. So this would be a goodness of fit test. And so which one of these would be good for the null hypothesis? The problem with A, even though they're saying they're all equal to each other, they're using the mu symbol. We don't want to say the mu symbol. We don't want to say anything about observed counts for the null hypothesis. So that wouldn't be the correct one either. It says flavor preferences are evenly distributed across the 4 flavors. I'm thinking that sounds pretty good to me, because if I'm trying to see which one is higher, I would want to assume that they're all the same. And I like that it talks about a distribution, evenly distributed. Let's go ahead and read the other ones just to see the issue. It says at least one of the 4 flavor preferences is different from the other 3. That would be a good alternative hypothesis, but this one's asking for the null hypothesis. And then the last one, the observed counts are equal to the expected counts. That's obvious. That's also not a null hypothesis. So in this case, we would want to assume that the flavor preferences are evenly distributed. And if we needed to write an alternative, this would be a good alternative hypothesis. And again, this would be a good example of a goodness of fit. We want to take our sample and see if the sample fits into that data. Now, number 2 says, which of the following conditions, which of the following are conditions that must be met in order to test this hypothesis using a chi-squared test? Think about the plan step. What is it that we need to cover? Remember, we need to cover random sample and sometimes the 10% condition if you're randomly selecting. And then really from there, it's just the large sample size condition. So is this part of either of them? If P is proportion of gum chewers in the population, looking at n times P and n times 1 minus P, that all has to do with proportions in 1 sample and 2 sample proportion test. That's not for a goodness of fit test. Now, option 2 says all expected counts are greater than 5. Well, that's for the large sample size or the large counts condition. So yes, that one needs to be fit. And individual observations are independent. Now, you might be questioning this one, but think about every time I talk about the 10% condition, why do we do that? It's to try to show that one person is totally separate than another person, that they're not affecting each other. So this is actually what the 10% condition is covering. So you want individual observations to be independent to each other. So that one was kind of tricky. If you could at least identify that option 1 was not correct, and you know that option 2 was correct, then you're on the right track. But option 3 is also important as well. So the answer to that one would be B, 2 and 3 only. All right, let's look at the number 3. Which of the following represents the component for the chi-squared statistic for wintergreen? So what I'm going to go ahead and do is go back up to my chart and look at wintergreen. Sorry, I don't know why it did that. Wintergreen. So first of all, I need to know what my expected counts are. Remember, because in option 1, we are trying to say they're evenly distributed. If there are 80 people who say they chew gum regularly, well, 80 people divided by 4 would mean we're expecting 20 in each of the flavors. That's what we would expect if they're evenly distributed. So I'm going to say that those are all my expected counts. Now, question 3 talked about wintergreen. So remember, this is the observed and this is the expected. So 22 is observed, 20 is expected. Now remember the formula. It's observed minus expected squared divided by expected. So if my observed is 20, it can't be these two because those start with 22. My observed is, oh, no, actually, JK, my observed was 22. I was thinking the wrong one. So it's got to be one of these two. It has nothing to do with square roots. It has nothing to do with the actual count because that's the observed count. So observed minus expected divided by expected. Do these two numbers match? No. So this can't be the answer. Observed minus expected divided by expected. It looks like E is the correct option for that one. Okay, let's go ahead and move on to number 4. Do male and female children respond differently to colors? A study of color association in children asked separate random samples of male and female 4th graders what emotion they associated the color red. Here are the results for each group. Now, I know the question doesn't ask this, but I'm going to ask you right now. Do you know what kind of test this would be? If I say a separate random sample, you should be thinking homogeneity. We will be comparing males to females. Because we're taking separate random samples, it should be a homogeneity test and a comparison of male and females. So with that being said, look at question 4. It says, which of the following would be an appropriate null hypothesis for this test? Well, if it's a homogeneity, the sentence frame I gave you is the null hypothesis is there is no difference between population 1 and population 2. So which of those sounds the most likely? Is it A, the distribution of emotional associations with the color red is the same for male and female? I feel like that's sounding pretty good. We're assuming that male and females are the same, which is kind of what my sentence frame says. So I'm going to go ahead and keep A in mind. What about B? Gender is dependent upon emotional association with the color red. No, that's not the null hypothesis here. Remember, with the null hypothesis, we have to assume that males and females are the same. What about emotional associations with the color red are independent of the gender? Now, that one kind of sounds good, saying like, it doesn't matter what the gender is, but really this is just trying to tie in gender together with emotion. So that's kind of trying to set it up for an independence test. Option D, the number of observations in each cell is the same for each emotional association. No, we're never talking about the actual observations in the null hypothesis. And then option E, 25% of the 4th graders associate the color red with each of the 4 listed emotions. That's not sounding like a null hypothesis to me. Where they're getting that 25% is probably from kind of the expected counts, but that's not how you write a null hypothesis. Even though this is not using the same sentence frame that I typically give you, the sentence frame, again, was that the distribution of emotion is the same for population 1, female, and population 2, male. The distribution of emotion with the color red is the same for the male and female. So yeah, A is the great answer there. Okay, question number 5. Under the assumption that the null hypothesis is true, which of the following represents the expected count for female children who associate with the color red with love? Okay, so notice we're talking about female children with the color red with love. Okay, female children and love. It wants me to figure out the expected count. So let's go back up to the table, and we're interested in females who associate red with love. So in other words, this is the observed count. We have to figure out the expected count. Well, remember, to do that, you do the row total, 102, times the column total, 77, divided by the grand total, 214. And so I feel that's actually how they had it set up for us. I had mine as 102 and 77. They just switched it around here. So this is their column total times the row total divided by the grand total. So you didn't actually have to even calculate it out there. You just had to kind of plug in the values. But option C is how you would figure out that expected count. Now, number 6, it says the chi-squared test statistic for these data is chi-squared equals 4.629. Which of the following intervals contains the p-value? Now, the reason they give it to you as intervals is because if you were using the chart that I gave you in your manila folders, the chart gives it to you as a range of p-values, not an exact p-value. But since I didn't teach you how to use the chart, I would just type it into the calculator. Remember, what you're going to have to use is, once you know your chi-squared test statistic, what you're basically saying is that's where we're located on that skewed distribution. Remember that chi-squared distribution. So in this case, chi-squared is at 4.629. So you got to figure out the p-value, that shaded region under the curve. So because we're talking about this in a chi-squared distribution, we're going to look at the chi-squared CDF in the calculator. And remember, we're going to type in what's the lower bound, what's the upper bound, what's the degrees of freedom. Okay, so that's the information that we're going to plug into the calculator. So let's go ahead and take a look at my calculator so I can refresh your memory how to do this. Because we're looking at a chi-squared distribution, you want to go to that distribution button. So I'm going to say second distribution. You're going to want to scroll down all the way to option 8, not 7. You want 8, chi-squared C df. Now, if you have the new calculators, you're going to type in the information that they gave you here, 4.629. And then the upper bound is just a really big number, like 999. And the degrees of freedom, I guess we need to go back to that and figure out the degrees of freedom. Let's scroll back up to the top. Remember my little trick I taught you. Cancel out one of the rows. Cancel out one of the columns. Notice my degrees of freedom, 1, 2, 3 data pieces left. So with 3 data pieces left, the degrees of freedom is going to be 3. So my lower bound is the 4.629. Upper bound is 999, degrees of freedom of 3. So looking back at the calculator, I'm going to change this to a 3. If you have the older calculators, remember you just have to put it in there with commas between each one. Man, I'm having a hard time talking today. When I hit enter, here's the p-value. It's about 0.201, so just a little over 20% basically. So let's go back to this, and we just got to figure out where does the p-value, remember what I just said the p-value is, the p-value is 0.201, where does that fall within this range? Well, this is saying between, that's a really small number and another small number. The p-value is not between those. In fact, these are the larger bound. My p-value is bigger than this one. My p-value is bigger than this one. My p-value is bigger than 0.1. In fact, that's what this is saying. The p-value is greater than 0.1 or 10%, because notice it's 0.20. So E would be the correct answer. My p-value falls best in this inequality, okay? All right, let's look at number 7 and 8. So state traffic engineers wanted to characterize the types of vehicles found on 3 state roads. They take a random sample of vehicles on each road over a 2-week period and get the results in the table for the number of vehicles for each type on each road. The engineers perform a chi-square test of homogeneity using the null hypothesis that there is no difference in the distribution of vehicle types on the 4 roads. So basically they took a random sample of cars, they took a random sample of SUVs, and they took a random sample of heavy trucks and trailers, and they're comparing those amongst the different routes that they're taking. So question 7 says, for this chi-squared test, what are the correct degrees of freedom? Well, again, if you want to use the degrees of freedom formula, you can use rows minus 1 times columns minus 1. That's technically the formula, but since it's rows minus 1, I just chop off the bottom row. Since it's columns minus 1, I chop off the one column and I count how many data pieces I have left. 1, 2, 3, 4, 5, 6, which tells me 6 is my degrees of freedom. If you're using the formula, notice we've got 1, 2, 3, 4 rows. 4 minus 1 would be 3. How many columns do we have? 1, 2, 3 columns. 3 minus 1 is 2. 3 times 2 is 6. So it gives you the same answer. It's just if you want to do the math or if you just want to kind of sketch out the answer through that chart there. Number 8 says, use that scenario. Below are the individual components for the chi-squared test statistic. Remember, the components are the comparison between the observed and the expected using that formula. So they use the formula on each of the components. These are all of those components. So to calculate the chi-squared, all you'd have to do now is add those all up. But what does it say in question A? Based on the original data and the components, which of the following statement is true? Part A says the observed count of heavy trucks and trailers on Route 176 is much higher than the expected count. Well, again, this one's going to take a little bit of looking around and calculating some things. They're talking about the observed counts of heavy trucks and trailers on Route 176. So let's look at heavy trucks and trailers on Route 176. That would be 24. Now that is the actual count. We actually have to figure out the expected count in order to know if the observed is larger than the expected, because that's what it's asking. Is the observed higher than the expected? You can see the difference, you can see the difference is 11.1, but we don't know if that's a positive or a negative difference. So to figure out those expected counts, what I did is I figured out the totals for us all already so that we didn't have to go through the process. And so to remember to find the expected counts, I'm going to do 474 times 131. I'm going to divide by 1328. And by doing that, I get my expected count of 46. So what do you think? Down here it says the observed count is much higher than the expected count. Is the observed higher than the expected? No, it's the other way around. The observed is smaller than expected, which means A can't be the answer. What about B? B says there are many more light trucks on Route 9 than we would expect if the null hypothesis were true. So again, we have to look at the expected value for light trucks on Route 9. So light trucks on Route 9 is 42. So we're talking about this one. Again, we have to figure out the expected counts. So to figure out this expected count, do the same thing. Total 184 times total 171 divided by grand total 1328. When you do that math, this expected count is 23. So remember, it says the number of observed cars on Route 116 is much lower than we would expect. Actually, I'm sorry, I'm reading the wrong one. There are many more light trucks on Route 9 than we would expect. Are there more actually on Route 9 than what we would expect? Sorry, I got interrupted there. There are more light trucks on the road than we would expect if the null hypothesis were true. Well, that looks right. There's more than what we would expect. Remember, this is the expected number. So that's looking like the right answer to me. I think that's looking pretty good. In fact, I'm going to go through here, and basically the rest of these you can kind of figure out that they're wrong. Like option C, the number of observed cars on Route 116 is much lower than we would expect. You would do the same process. You would figure out the observed and expected, and you're going to see that it's not quite the correct one. Same thing here. The greatest difference between observed and expected is for heavy trucks and trailers. Now this one, actually talking about the greatest difference, that's going to be the biggest component. Looking at the largest component, this is the largest component here. For light trucks and Route 9, that's not the heavy trucks and trailers. Like, that's a large component, but that's not the largest component. So again, that's not the answer. And then E, the chi-squared test statistic for this test is less than 30. To figure out the chi-squared, you would have to add all of these up together, and it ends up being greater than 30. So it doesn't end up being that answer as well. So this is the correct answer, because when you compare the light trucks on Route 9, when you compare the observed to the expected, it matches what this one is saying here. Okay. All right, number 9, are all employees equally prone to having accidents? To investigate this hypothesis, a researcher looked at a light manufacturing plant and classified a random sample of accidents by type and by age of employee. Okay, this top one here is the expected count. Okay, let's see. Actually, JK, sorry, I'm reading this wrong. These are the observed counts here. Okay, they gave us a table of observed counts. It says here are the expected counts. Those are these values here. So 9 is observed, 18.5 is expected. 61 is observed, 51.5 is expected, and so forth. It says, what's the individual component for the chi-squared test statistic for the cell under 25 and burn? So which one is that? Under 25 burn, under 25 burn. So what we have here is this is the observed and this is the expected. If you're trying to calculate the component, you do observed minus expected squared divided by expected. So you would do 17 minus 7.9 squared divided by 7.9. So you do that value out in your calculator and you should be getting 10.48. Okay, let's look at the very last multiple choice question. Children of 3 ages, 5, 7, and 9, were given a list of 5 different animals and asked which animal they would choose if they could be that animal for one day. A chi-squared test for homogeneity on the data produced a test statistic of chi-squared equals 13.89, which yields a p-value of 0.0847. Using a significance level of alpha of 5%, which of the following is the appropriate conclusion for this test? You guys, really, the only thing you need to know here is what the alpha level is and what the p-value is. That's going to help you make the decision, right? So if the p-value is 0.0847, isn't that larger than your alpha level at 5%? That's larger than your cutoff. So does that lead you to reject the null hypothesis or to fail to reject the null hypothesis? You should be thinking fail to reject. So let's take a look. It's not going to be rejecting. We never use the phrase accept the null hypothesis. We don't reject the null hypothesis. So that leads us to D or E. Both of these are failing to reject. So we got a C. Does that mean there is convincing evidence that the distribution is the same for the three age groups? Or there is insufficient evidence to conclude the distribution of animal choices is different for at least one of the ages of groups? Remember, if we are failing to reject, there is not enough evidence to conclude the alternative. So E is the answer for that one. And so that concludes the multiple choice. Take a look on Schoology for the free response portion of the video.